In numerical analysis, the trapezoidal rule is a technique for approximating the definite integral. The trapezoidal rule works by approximating the region under the graph of the function as a trapezoid and calculating its area. It follows that applicability and alternatives. The trapezoidal rule is one of a family of formulas for numerical integration called Newton-Cotes formulas, of which the midpoint rule is similar to the trapezoid rule. Simpson's rule is another member of the same family, and in general has faster convergence than the trapezoidal rule for functions which are twice continuously differentiable, though not in all specific cases. However, for various classes of rougher functions, the trapezoidal rule has faster convergence in general than Simpson's rule. Moreover, the trapezoidal rule tends to become extremely accurate when periodic functions are integrated over their periods, which can be analyzed in various ways. For non-periodic functions, however, methods with unequally spaced points such as Gaussian quadrature and Clenshaw-Curtis quadrature are generally far more accurate. Clenshaw-Curtis quadrature can be viewed as a change of variables to express arbitrary integrals in terms of periodic integrals, at which point the trapezoidal rule can be applied accurately. Numerical implementation. Uniform grid for a domain discretized into n equally spaced panels, or n+1 grid points, or equals x1 less than x2 less than xn+1 equals b, where the grid spacing is h equals n. The approximation to the integral becomes non-uniform grid when the grid spacing is non-uniform. One can use the formula error analysis. The error of the composite trapezoidal rule is the difference between the value of the integral and the numerical result. There exists a number xi between a and b, such that it follows that if the integrand is concave up, then the error is negative and the trapezoidal rule overestimates the true value. This can also be seen from the geometric picture. The trapezoids include all of the area under the curve and extend over it. Similarly, a concave down function yields an underestimate because area is unaccounted for under the curve but none is counted above. If the interval of the integral being approximated includes an inflection point, the error is harder to identify. In general, three techniques are used in the analysis of error: Fourier series, residue calculus, Euler-Maclaurin summation formula. An asymptotic error estimate for n infinity is given by further terms in this error estimate are given by the Euler-Maclaurin summation formula. It is argued that the speed of convergence of the trapezoidal rule reflects and can be used as a definition of classes of smoothness of the functions. Periodic functions. The trapezoidal rule often converges very quickly for periodic functions. This can be explained intuitively as, when the function is periodic and one integrates over one full period, there are about as many sections of the graph that are concave up as concave down, so the errors cancel. In the error formula above, f equals f, and only the O term remains. More detailed analysis can be found in rough functions for various classes of functions that are not twice differentiable. The trapezoidal rule has sharper bounds than Simpson's rule.